Welcome to Class Time, your daily classroom for CSEC and CAPE subjects. I'm Leo Lewis, your CSEC IT teacher for this session. Today's topic is programming. Yes, the dreaded programming. Now, I know that sometimes it's pretty hard for some students to grasp the idea of programming computers. What is important to understand is that you're working with a computer, you're working with another device. And the way how we understand things, or the way how we might frame the world is different from how the computer frames the world. And so if we're going to frame the world according to how the computer works, then we have to understand its language. And so as a student, you have to divorce yourself from how you understand a problem or how you understand a solution. For example, if you're possibly finding the square root of some value. All you plug something into the computer and press the square root button. It's a different case with the computer. You have to tell it what a square root is and how to go about calculating each step of finding a square root. So you have to give it all those minuscule details. But what we're going to be focusing on is the importance of writing programs and how we go about writing programs. So in this particular section of your syllabus, yes, you look at about a number of things relating to low-level programming languages, high-level programming languages, and they are pretty easy if you take the time. All right. For specific objectives 1 and 2 in section 8 of your syllabus, you should be able to distinguish between low-level and high-level programming languages. And you should be able to describe the sequence of steps of implementing a programming language. So we today will be looking at high-level languages as opposed to low-level languages. What's their benefit? What's their differences? And then, according to specific objectives 4 and 5, we should be able to declare constants and variables using elementary data types, and then translate algorithms to statements of high-level language. And of course, the high-level language that you should be using is Pascal. If you are a ComSci student and you're listening, you might be using C, but the idea is that you're using a high-level language and possibly what is called an imperative language. All right? So what we'll be doing today, essentially, is we're going to be looking at the history of programming languages, the programming steps required for compilation and interpretation, and then some features of Pascal. What you should already know is some idea of what it means to do some kind of problem-solving steps, all right? You should be acquainted with problem-solving steps. You should, of course, be acquainted with pseudocode. You should be acquainted with flowcharts. Now, if you're not, let me just give you a quick rundown. What a pseudocode is, let me start with algorithms. What an algorithm is basically a set of steps that outlines the solution to any kind of a problem. Your pseudocode and your flowcharts are a way to represent those solutions or that algorithm. Now, a pseudocode is basically what you'll write like English language statements mostly. And your flowchart would represent graphical or have a graphical representation of what that solution is. So if you have done those, great. This will be a walk in the park for you. All right, so what are programming languages? Essentially, programming languages are any set of instructions, normally in some kind of language created by someone that you use, or you would take those instructions and give the computer these instructions in order to solve some kind of a problem. And whenever you think about it, you might be using Pascal, and then in Pascal you have these several different structured instructions that are basically pre-packaged for you, and you are given rules to use these different programming languages or these different statements. And so anytime you hear a programming language, whether it is Java, Pascal, C, whatever it is, you're given these rules and you're given these instructions, and each of these instructions have to abide by these rules, and that is why we call it a syntax. So if we have a certain kind of instruction, the instruction has a certain kind of rule that it has to follow, and that is what we call the syntax, all right? So why do we use programming languages. I'm sure some of you who might be nerds like myself to some degree, you have heard of the Mars rover. And you might be wondering, what on earth does this have to do with programming? Well, the truth of the matter is, according to Yerka, I think his name is, there is an actual piece of software or programming language created so that they could program the rover. And one of the good things about this particular programming that happened with the rover is that because Mars is kind of uncharted territory, and scientists are not sure what's there, or even not sure what to study, the rover has been programmed to decide what it wants to study, or where it needs to go, and what it will study there. Part of the, I guess, wonderful part of it is that on the rover there's what is called a chem, and that cam has been programmed by somebody to send out light beams or send out lasers, and basically just to burn different rocks. And based on the emissions that come from those rocks, sensors are used to pick up the information as to the composition of the rocks. Now, I thought about this and I'm like, goodness gracious, you mean that we actually have this kind of technology around? Well, yes, we do. And behind all of that is this programming language called Autonomous Exploration of Gathering Increased Science. Now, I don't know about it, kind of long, but that's the programming language that is used with with this Mars rover. But again, the technology is going so fast, and it is important that we who are studying IT are able to actually write programming languages for these things. Now, you might ask, what does that have to do with me? Well, here is something a little bit closer. Your phone. Most of us, if not all of us, our phones are created with Android or with the Android OS. And this Android OS is programmed. Every single application that you download has been created in the Android Studio. And behind the Android Studio, or behind the application, is some kind of a Java program or Kotlin program. Now, I've done a couple of apps myself, and sometimes it can get tedious. But the idea is we are creating these things for the betterment of our lives. And so when we create software, it's about creating something useful and programming the computer or the phone or whatever we want to use so that it helps us eventually. And we, of course, we are working with tablets now, we are working with phones now, and some of the things on it might not work properly. And the truth of the matter is sometimes programs don't work as we expect them to. And if they don't work as we expect them to, what it means is that we need to do some troubleshooting. We might have to send back to the app store or reinstall some kind of patch or something of that nature because somebody found a bug or there is a bug that needs to be fixed. And whenever a bug needs to be fixed, some programmer has to go in there and fix that particular bug. So we know where we're going or where we've been with programming languages. We know more or less what these devices are going to be used for. But you need to also understand why we're at this point with programming languages, okay? And so we need to possibly take a quick look back at where we're coming from. Now, there are basically two categories, according to your syllabus. There is low-level first and foremost. And your low-level languages take in generations 1 and 2. And we're going to be explaining what those are in short order. And here are some of the characteristics of your low-level languages. One, they are machine-friendly. In other words, as long as you write a piece of code inside of this or using these low-level languages, the machine or the computer finds it easier to execute them. All right? The difference or the problem with that is that we as humans tend to not understand that machine language. And then it's machine dependent, meaning that if we create code for one particular computer, then it might not work on another. And so you might, well, when you start up your computer, you might just say Windows 10, but years gone by, we'd normally some running things on the screen that would tell you that your processor is x86 or something of that nature, telling you the type of processor or the type of instruction set that is behind your working machine. And what that means is that basically, if we create a piece of code for, let's say, Mac, right? If you create that kind of a code for Mac, it will not work on a Windows machine. And so whenever somebody creates a chip, whether it be a RAM chip, whether it be a CPU chip, whatever it is, they have to create their own kind of low-level language behind the chip or that runs the chip. And so that's why we call it machine dependent. It's dependent on whatever computer we're putting it on. It's executed directly or firstly assembled. Now what this actually means is that because it's so close to the machine in terms of the execution process, it's very, very fast. And we'll see why it's very fast a little bit later. And finally, as we said, it's hard to write. Humans who are able to write machine code are a dime in a dozen these days. But very early when the inception of computers came to the fore, a lot of people had to write machine code, all right, or low-level language. The first one is binary, or as we said before, machine code. Some of them you might already know about: ASCII, EBCDIC. I think the syllabus 2 years ago included some of these things in it, but I'm introducing it to you so that you can understand what we're working with when we talk about machine or binary codes. These codes, of course, had to be interpreted by the persons writing the code themselves, or the persons writing the code had to know what these codes were like. Let me just show you quickly what that means. Here is the ASCII code for capital A. It's 0, 1, then 5 zeros, then another 1. And capital B is 0, 1, 4 zeros, 1 0. As you might can see, if we're working with binary, for those of you who have been doing some binary before, or possibly from second form, third form, if you add a 1 to the value of A, then you'll actually get the value of B. And so programmers who wrote in ASCII code had to have a chart or had to have an understanding as to what these things are. Also, you might have learned about punched cards. And punch cards were actually large, well, not large, but medium-sized kind of cards that had holes in them that would represent these different kind of characters. Another set, common A and common E. And if you notice, common A is actually different from capital A, because in the mind of a computer, whatever the character is, even if they seem similar, they have to be given different codes because the computer will be treating them differently. Case in point, plus has a code of its own, 001, 01011, and then the question sign also have a code of its own, 00 and then 5 ones. And then finally, the greater than sign and the less than sign have their own kind of codes. All right? So it's clear that if you were supposed to write some programming code in this machine language, your knowledge of it has to be quite extensive, especially if you're going to write a lot of text or you're going to do some form of calculation. Your knowledge of it has to be quite extensive, and that is the downfall, and that is why we continued as human beings to try to refine what we did or improve on these programming languages. All right? Just a quick look back. Some of you might have remembered the use of, we call them bistable devices. And these bistable devices are basically devices that store charge, essentially. And what they are, they will stay in one state until told to change. And those of you who might be doing ComSci, you will learn about flip-flops, and others, etc., etc. And what these are basically devices that run on electricity. But because we understand 0 and 1, the 0 and 1 translate to no electricity or electricity. And so the pulses that take place or the electric signals that take place in your computer will have some kind of a representation that translates to zeros and ones. All right? The other low-level language is what we call assembly. This was a little bit easier because it just used different kind of what we call mnemonic codes, which are just shortened forms of words that helped us to understand what we wanted it to do. This made the writing of code easier, but then it was still machine dependent. In other words, if I created a chip, I have to create the code that runs the chip. And whenever you create code on your own, you have to be very, very careful as to what the code does. In this case with assembly, why you have to be careful is that normally assembly code, well, almost any code, or whatever the case is, will manipulate your computer's CPU registers. So the registers that are inside your CPU are used when you are writing assembly code. And just to show you that really quickly, here's a picture of a code, and you can immediately see where we have this word MOV, and that MOV just stands for move. And then we have what are called the operands and the value after MOV. So if we look on the line just after start, we have MOV, RO, comma, hashtag or number sign, 10 or 10. So MOV means that we're going to move to the register R0 the value of 10. So, and if you notice, if you're following through, you will see where we have another MOV that says we're going to move to register 1 the number 3. And then we're going to add RO, that means that's the resulting register, but we're going to add R0 to itself. And we're going to add R0 to itself, or R0 to itself, and then R1. So in other words, we're going to make an addition with 2 variables or 2 values using 2 registers. And this has taken up about 3 different lines. That is the case with assembly. You have to specify what you're moving into what register, what you want to do with what is in the register, and then make sure you give some kind of an output. Whereas you might be working with a Pascal or a C where you just write out a variable equals whatever plus whatever. That's fine, right? That's a high-level language. This, on the other hand, assembly, you have to stipulate every single move, every single value, and then when you're finished with the program, you tend to have to free that register space. And that's why working with assembly was considered so very technical and possibly dangerous for your computer. Because if you don't deal with the spaces themselves, if you don't deal with the registers and clear them, when you're finished with a program, you run the risk of leaving the values there and running out of register space for your computer to use. All right? So that made us move on to the second category, which are basically high-level languages. And these high-level languages span generations 3 to 5. And as you can already guess, they are a little bit more human-friendly, a little bit more, because some of us still having problems with Pascal. They are machine-independent, meaning that if you have a programming language on a Mac or on Android, they tend to be the same kind of a language. For example, if you get a Java interpreter for Windows, it's the same kind of Java or the same Java that you'll use in the Android Studio. So your understanding of Java can be brought from one machine to the next. So it's machine independent. So as long as you learn Java and you can learn the packages inside of Java, you can carry it over to the other machine. All right? They are normally converted to assembly, or they are converted directly to ones and zeros. And those are basically 2 different kind of operations. We call one interpretation and the other compilation, which we'll be looking at the next couple of slides. And then, of course, the execution is slower. Why? Simply because you have to convert from the high-level language to zeros and ones. It doesn't mean that it's slow. It just means that it's slower than assembly. So even though you might be writing like 100, 200 lines of code, your computer is still fast enough to handle that amount of lines of code. And of course, sometimes it depends on your instruction set. So those of you who are doing ComSci who might be listening, again, I'm going across syllabus or syllabi. If you're doing that, you'll learn that RISC and CISC or those instruction sets are created so that you can basically work with a computer of different word sizes. And sometimes you can notice the speed at which they're executed. All right, so according to your prescribed text, which is written by Gay and Blades, I think, there is a picture there that will give you a complete understanding of how interpreters work. First and foremost, you'll create the source code, and that source code essentially is just like you typing code in Pascal. So that is your source code, right? That's where you put in the instructions to be typed or the instructions for the computer to follow. So that's your source code, right? And that is typed in an editor. And then it is run through an interpreter. Now, what the interpreter does is that it takes each line of code separately and executes. So that interpreter takes one line, changes it to zeros and ones, and then gives you a result. If there is an error, that error will not be discovered until that line is reached. And so your interpreter is always going to execute each line. As it comes, execute, comes, execute. And then when there's an error, then it will stop the execution and head back to the editor so that you can fix that particular error, all right? So that is how your interpreter works. On the other hand, for like Pascal and C, for those doing ComSci, it would be C. For those doing, of course, CSEC, it's Pascal. The source code or the program code has to be compiled. And that compilation process will take several different steps. I'm just going to mention a couple of them. There will be a lexical analyzer, which basically looks at the code and looks at each instruction of the code and ensures that the syntax in that instruction of the code makes sense based on what it has predefined. So if you typed print instead of printf in C, or you type print instead of write or write ln in Pascal, your compiler is going to flag it and says, hey, listen, I do not know this. Either define it as a variable or change it because this function, I don't understand it and I can't go any further. So with your compiler, everything has to make sense to the programming compiler before any execution can take place. And that's one of the benefits of working with a compiler, because I tell you the truth, if you were working with an interpreter, you would have to be, and you're making a lot of errors, you'd have to be continually going back and forth between execution and editing. With your compiler, it forces you basically to stay in the editing mode until everything is just right. And when that is right, or when all of the syntax errors are gone, and again, your syntax error is an error that basically occurs because you did not adhere to the language rules. When that is done, then it will possibly create an object code, and that object code is where we get into the zeros and ones, which sometimes you'll be able to just click on it depending on what it is. And then it will create an executable that you can double click on and the program will run. However, what happens is that the biggest problem essentially when you reach this stage is that if there were runtime errors, like for example, you might have did something wrong with an array, or you didn't reference an array correctly, or something of that nature, then what happens is that a runtime error might occur. All right? You're running the program and you think everything is all right because you have no syntax errors, but then you're told, hey, this problem occurs. That's a runtime error, an error that happens during the time that the program is running. And when that happens now, you are directed back to the editor again for you to fix whatever happened in your program. Whenever you're finished with all your logic errors, or you've done debugging and you've finished with the errors, you might now end up with a working program. And that working program you can execute off the bat anywhere you want. And it tends to be an executable file depending on how you work your compiler or how you have changed your compiler's environment. All right? Now, how do you create your source code? Well, in Pascal, there are a couple of things that you would want to pay attention to from the get-go. How you start your program, the declaration and initialization of variables and constants, use of read and write in your program. So these are some things that we're going to be looking at as well. Also, you'd want to pay attention to how you work with selections and loops. So let's look at the first one, the structure of your actual code. All Pascal programs begin with the word program. But after the word program is written, you need to give the program itself a name. So you are going to write the word program or type the word program, and then you'll give the Pascal program a name followed by the semicolon. So that is the start of it all right? And that has to be placed in your program or in your editor. Then below that, you'd want to declare or initialize your constants and your variables, all right? And again, Pascal is a compiler, and just like C, well, there are a couple of differences. It is important that you declare all constants and variables before you use them, all right? Because that can be a warning sign, or you get a warning sign from the compiler. And then you have begin and end, wherein all the execution takes place, all right? So again, just to repeat, all Pascal programs start with program and the name. Then we declare your variables and your constants, all right? And then you have the begin section, all right? And of course, your begin section begins with begin, and your end section, or the part that ends the program, is end full stop. Don't leave off that full stop. That full stop is important, all right? So let's look at writing or printing on the screen. When you're printing something on the screen, you'll want to use the keyword write, and then you'll have another set of syntax to follow, which includes opening parentheses, opening single quotation, the text itself, close single quotation, close parentheses, semicolon, and that's your write statement, and that prints something directly on screen. You can use write ln as well, and write ln just simple prints the thing on screen and then puts the cursor in the line below that statement that was printed. So that's the difference between write and write ln. And please, I'm going to ask you, whenever you're doing your program, make up your mind which one you want to use and how you want to use it. Why? I've seen students use write all the way through, and then when the program came out without any spaces, they were like, where are the spaces? And I'm like, you need to use the write ln if you need spaces, all right? And then sometimes you'll forget that it is write ln and type write n or write one n. It's important that you just pay attention to all these, all right? And then, of course, there's another convention where you want to print something from a variable. And if you want to print something from a variable, the key thing is to have that variable inside the parentheses, but not inside any quotation marks, all right? Because you're printing the value that's in the variable. So if it's a name that you want to print, you're not going to put the word name in quotation marks. You're going to put just name inside the parentheses, and that should suffice. Then when you want to get user input, you'd want to use the word read. And that goes across pseudocode as well as Pascal. You can use this in your pseudocode if you feel the need to. All right? So you have read, open parentheses, and then the name of the variable, close parentheses, and semicolon. All right? You can use read ln as well. And it's the same kind of convention, you know. You type, you'll see something printed on the screen, read ln, and it actually is in the next line for the entry to be made. All right? And then there's one other convention that we tend to use is just put a read ln and semicolon just before the last end statement of your Pascal code. And what that does is just to ensure that the user has to press some key to get everything off the screen. And that is important because that pauses all that is done on your screen. If you don't put it there, what will happen is that the program will run and then leave your screen. But what you want to do is to keep it on the screen so you can see and check what you're doing. So the read ln pauses everything on screen. All right, now your declaration of your variables. Pretty key. Your variables start with, or the declaration starts with var. Pretty simple, just remember the first three letters. And again, this comes after you make the program declaration or the program name, right? And then below that, you'd want to put in the name of your variables, colon, then the data type of the variables, semicolon. So in one case, we can have name, colon, string, but in this case, we're declaring two string variables. So we can have name, comma, address, colon, string, semicolon. All right, so you can declare a number of variables in this way by just comma separating them. All right, or you can just declare them one at a time, whichever one works for you, but just make sure that you're doing it in a systematic way that you can understand as well as the computer can understand. So we have declared name and address as strings. We have declared salary as real and a real number, right? Well, hoping that you are remembering most of your math laws. A real number is any number that can be represented as a decimal or a fraction. So any number is a real number, essentially. And so we normally use real numbers when we want to work with decimal places. So salary, in this case, is going to be a real number because a person's salary might have cents, right? And cents comes after the full stop, okay? And so salary would be real, and then age might be an integer. We're no longer children, so we don't recognize 3.5 and all those things. So an age is definitely an integer. You're either 12 or 13, or you're either 16 or 17, not 16.5. So age would be an integer. And if you notice, we are working with 3 different data types here. Normally, or years gone by, we would have marked you for the 3 data types. It might not be the same this year, but check your syllabus just to make sure. But you want to be sure that whenever you're working with your solutions, whether you're SBA or you're just trying to practice, you want to be sure that you're able to work with all 3 data types, all right? Then we have the actual initialization of the variable. So we are seeing here now where variables are both declared and initialized separately. And this initialization of all the variables takes place inside of the begin or just after the begin, all right? Make sure that you initialize all the variables. You do get marked for something like that in your SBA, all right? So the first initialization is name equal employee, salary equals 0.0, semicolon, age equals 0, semicolon. But there are some errors here. And if you're watching, you should be able to spot some of the errors. All right? There are a couple of them, but we're just going to look at one in particular. The error is that in Pascal, equal is used in a completely different way from how we understand equal. This name equal employee, well, other than the quotation marks being wrong, this is a completely different kind of equal. What we are doing is setting name to be the word employee. And so we have to use a different type of equal sign. And this is where some people tend to get it wrong for their SBAs or for their actual working on their assignments or wherever. Whenever we're working with equal in Pascal, it has to be a colon, then an equal sign. And that is the kind of equal. You normally call it an assignment, all right? Some of you might have used an arrow in pseudocode. It's the same thing. In Pascal, we use a colon, then an equal. Don't forget that. When we look at the declaration, of course, of constants, we will see where the equal is used for that particular constant variable. In this case, we have const tax equal 0.11. And this constant being declared just after the begin means that we are setting this tax value to 0.11. And that means simply that wherever we see tax, it's going to be 0.11. And the program nor the user can change this constant value. As opposed to the variables, you can change them using the program code, or the user can make some kind of an entry. But with a constant value, you can make no changes whatsoever. And this can be critical depending on what you are doing in your program. Again, if you want to change this value from the declaration, that is fine. That can work. But as the program runs, this value will never change. And you can, of course, decide on what you want to use that for. Then we have selections. And there are 3 types of selections that your your SBA might be looking for, or your whoever is marking your SBA will tend to look for. They're looking for if, then, else, or they're looking for case statements. In this case, we just look at a simple if, then, and you can, of course, theorize or think about it in the form of just making some kind of a decision. And it doesn't matter what the decision is, as long as you know how to represent it. In this case, we're looking at this select value, SEL equal 3, and the 3 is in quotation, so that might actually be a character, not a number. So if SEL is equal to 3, then right, you selected 3 semicolon. And notice that this semicolon is ending with the right line. All right? When you're working with your if statements of this nature, whether it's 1 or 2, then you would think about it as just having one line, and so 1 semicolon. So your then doesn't have a semicolon immediately after. All right? There's another then where we will possibly have more than 1 statement, and with a situation of that nature, or with an if statement of that nature, we want a begin and end to start the statements and end the statements. So if we have our begin, what that means is that coming inside the begin, we have several different statements that we want to be executed inside this if statement. So if you have several different statements you want to be executed, this is where you would take it. And then, of course, you end. The difference with this end from the last end is that we have a semicolon at the end of this end. All right? So whenever you have this if statement and you have more than 1 code lines that you want to include, you put your begin immediately after then, write your different lines of code with your semicolon, and then, of course, end your if statement with another semicolon.